All right, so as we continue on, we're going, I guess, with our last, with this week, I guess with our 10th week, the last topic I'll cover will be maybe just a brief intro into some numerical methods in computational statistics, and this is a topic that will be covered more deeply in 102B, but we'll get to the introduction. And before we can really talk about numerical methods, we have to talk about the machine representation of numbers, just because a lot of the calculations that we do in regular math just don't work out when you're using floating point numbers in the computer. Okay, there are some very very distinct things, and certain things that we take for as granted in regular math just don't apply. Okay, and so the key thing to remember is that everything in the computer is stored as ones and zeros, right? We've got bits. Everything is represented as bits, and then if you group bits together, you got bytes and things like that. But everything at its most base level is stored as a 0 or a 1. And so, we're used to decimal notation, and so we have 10 digits. We've got 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. But all of these, for binary is just a 0 or a 1. Okay? And so, and as far as the computer goes, you have to kind of allocate a certain amount of memory for the storage of a number. Okay, so when we're dealing with numbers, in day-to-day life, everything is unbounded, right? Like we could potentially have a number with 1,000,000 digits, and we can represent that. It would take a long time to write out, but we could do that. But as a computer, we allocate memory, and so a lot of times we'll use just a certain amount of digits. Okay, so we might have 8 bits, so 8 placeholders, 1, 2, 3, 4, 5, 6, 7, 8, and these 8 numbers can be used to represent an integer. Okay, so we have this is 8 bits, which is equal to 1 byte. Okay, and you use a little b over here and a capital B over here when you're abbreviating, and so we can use this to represent an integer. Okay, and so if we're doing integers, usually the first spot, this is used to store the sign. Okay, well, okay, I'm sorry. Let me go back. All right, so there are 3 ways to store integer values. Okay, we have the sign and magnitude. Oops. Okay. Okay, we have biased, and then we have a complement scheme. Okay, these are all different schemes to ways to store integer values. Okay, and so sign and magnitude, I think this one is kind of the most, quote, natural way to think about numbers, and so the first bit is the sign, and then the other 7 bits are the magnitude of the integer. Okay, and so the largest value you can have will be so this will be 7, and I think so 0 will generally represent positive, and then you'll have 7, 7, 1. So this would be so this is your 2 to the 0, and then just like decimal notation, okay, all the way up to 2 to the 7th. Okay, so the largest value you can have would be 2 to the 7th plus 2 to the 6th plus 2 to the 5 plus 2 to the 4 plus 2 to the 3. Okay, or you can think of this as 2 to the 8 minus 1. Okay, so this is the largest positive value. And then the largest negative value will be the exact same thing, except it will be -1 times 2 to the 8 minus 1. Okay, or 2 to the 7 plus 2 to the 6. So, this would just be like, maybe in high school you learned about different bases. And so when they said, convert something into base 2 or base whatever, this is probably what you did, right? You'd say the value 100, right? So 100 in decimal is equal to, what is it? 64 plus 32 plus 4, right? So this is 2 to the 6. And this is 2 to the 5th, and this is 2 to the 2. So this gets represented as 0 and then 1, 2. Okay, so I'd have to 0, 0, 1, 0, 1, 2, 3, 4, 5, 6. Something. Something like this, okay? I don't know, whatever I'm doing here. Okay, so et cetera, et cetera, et cetera. This is what we have. Okay, so that is that's with 8 bits, and then if you want to have even more bigger numbers, you can have 32-bit integers or 64-bit integers, things like that, and you can just have much bigger or smaller numbers. Yes. It would be 2 to the 7th. So you can have 7. So the first one is the sign, right? And then these other 7 are for the magnitude. So 0 would be 0, 0, 0, 0. And you'd have 2 representations of 0. You'd have a -0 and a +0. Is that okay? So that's sign and magnitude. So the largest with sign and magnitude would be, if you're using 8 bits, would be basically 2 to the 8 minus 1. You can't have 2 to the 8, though. Okay. I guess I'll save this. This will be stats. Okay. Then I guess the slight disadvantage of sign and magnitude is that one of the numbers is wasted because you got 2 representations of 0, which can also complicate things, because if you're checking for equivalency, you could have a -0 and a +0, and strictly speaking, when it's stored in memory, those aren't exactly the same, although numerically they are exactly the same, right? So that's so you have another scheme for storing decimals, and that's the biased scheme. Okay, and basically these numbers are just like, how much bigger is it than let's see. Okay, so if we have a 8-bit number, then the value 0, 0, 0, 0, 1, 2, 3, 4 would be equal to 2 to the negative 2 to the 8 minus 1. Okay, so this would be the minimum value. The smallest value in the 8-bit scheme is represented by all zeros, and then the largest value is represented by all ones. And this would be equal to negative 2 to the 8 minus 1 plus basically 2 to the 7 plus 2 to the 6 plus 2 to the wait, I'm sorry. This needs to be 2 to the 7 minus 1. Okay. 5 plus 2 to the 4, etc., etc., etc. Okay. And so I'm sorry. Let me just double check all of my math here. Yeah. Okay, so what is 2 to the 7th? 2 to the 7th would be 512? What? 128? Okay, so this would be negative 127, and then this one would equal to basically 127 plus all of these other things. Negative 127 plus, 128, and et cetera, et cetera, et cetera. So I think this ends up being 128. Okay, so you have basically a range from negative 127 to positive 128, whereas in the other scheme, the sign and magnitude, it goes from negative 127 to positive 127. Okay, so here it's just basically this number represents how much bigger is it than the absolute minimum of being negative 127. Okay. Okay, that gives you a total of 255 values that can be represented. Okay, and then the complement scheme is that this one's the weirdest. Well, not weirdest. You have all of these numbers, okay, and basically for positive values, this is this gets represented as basically positive. The first part is the sign, and then this is kind of the magnitude as far as positive values go. But then for negative values, the negative 1, okay, so negative 1 is represented as basically 2 to the 8th minus 1. Okay, so that's essentially 1 and then 1, 1, 1, 1, 1, 1, 1. Okay, so this represents negative 1, and then negative 2 is represented as 2 to the 8 minus 2. So this becomes 1, 1, 1, 1, 1, 0, 1. Okay, and so essentially for negative numbers, it's pretty much like how much more do we have to add to this to make it equal to 2 to the 8. Okay, you can kind of think of it as, for negative values, must we add to make it equal to the 8 or whatever, however many bits you have. So it's kind of the complement. So 2 would be the complement to this quantity to make it 2 to the 8. And so that's why it's represented, this is called the complement scheme. Okay, all of the internal storage as far as integers and things like that in R are done internally, and R doesn't really have any control over it. Okay. That said, when it comes to floating point numbers, we get some certain behaviors in R that are a little bit if you're not used to the machine representation of numbers, it can be unexpected. Okay, but if you think about it, if you just think about restricting yourself to decimal notation, then it kind of makes sense. Okay, and so for example, if I say, what is 1/3 times 3, you would tell me this is equal to 1, right? This is how math works. We know this. Okay, now if I said do this using decimals, okay, using decimal notation, you would write 1/3 is equal to 0.3333, and then somewhere along the way you'd probably just write ... or something. Okay, and then you could say, well, this is equal to, multiply that by 3, and you'd get 0.9999 ... which we know is equal to 1, right? So we know this. Okay, but this requires our mental intuition about math that says, oh, here I've got a series of digits going on forever. Okay, and with a computer, you can't say, well, store an infinite number of digits, because that would take infinite memory, and that's just not efficient. So maybe you limit yourself to using 10 decimal places. Okay, and so if we limit ourselves, to using 10 decimal places, what we'll have is 1/3 becomes 0. And then we would have 10 decimal places, and we would multiply this by 3, and we would get 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and this is not equal to 1, right? So we have there's no better, more accurate way to represent 1/3 with 10 decimal places than this. Okay, and the unfortunate thing is that when you multiply this by this, you get this. Now we can't store any other information. Okay, and so when you see a number represented like this, we don't know, is this 1/3 or is this actually a 0 with 3's up to the 10th decimal places with a bunch of zeros trailing it. Okay, so we can't tell the difference, and so when you multiply this by 3, you get something like this, and we don't know, should this be 1 or should this actually be this? And this is basically the problem. If you can expand this problem onto binary representation of numbers, and you run into the same type of thing. Okay, does this make sense here? All right, so is this equal to 1? Or strictly speaking, the answer is no. Okay, and so we can, when you do things in R, or when you represent things with numbers, you just run into the same kind of problem. Okay, so with binary notation, we have we have type double, right? This is our this is the default numeric mode for in R. And actually, this is it's a engineering standard here. It's detailed on this page. This represents how double precision should be represented. So it's kind of a standard, industry standard for floating point numbers in computation, and this page goes into a lot of detail. But basically, you have 64 bits to represent a floating point number. Okay, 1 is used for the sign, 11 are used for the exponent, and then the remaining 52, or I guess 53 spots are for, or no, 52 is for the mantissa, okay, in scientific notation, right? So all numbers are basically, so in scientific notation you would write in decimal. So if this is decimal, you would say this is 1.2 e times 10 to the 3, which is equal 1.2 e3 or e3, something like that. Okay, and with binary, you've got you're gonna have to represent things this way. Okay, and so this so if we have something like this, okay, this is basically 2 to the 0, and then this would be 2 to the negative 1/2, 2 to the negative 2, and 2 to the negative 3. So this would be equal to 1, and 2 to the 1/2 is plus 1/2, plus 0, plus 1/8. So this would be 1 and 3/8. So, oh, did I mess something up? Oh yeah, not 3/8, 5/8. So 1.625. Okay. And then so and then you'd have it. You can multiply it then by an exponent, 2 to the 0, 2 to the whatever. Okay. I'll just leave it as 2 to the 0, so it stays as this. But so this is we just represent our floating point numbers this way. Okay. But again, just because of the lack of being forced to have a finite number of digits, you get some strange, a few strange behaviors here. Okay, let me just cover a few things. So we have 1 bit for the sign, 11 bits for the exponent, and 52 bits for the mantissa, which is basically the non-exponent sign in the okay. And so as far as the largest and smallest values that can be represented, okay, let's see. So the first digit for the mantissa is almost always 1. Okay, and that's just because if you were just thinking about a decimal number, okay, if you wanted to represent the number 0.025 in decimal, you would not write it as 0 like this. In scientific notation, you would write 2.5 times 10 to the minus 3, right? And so because of this, the first digit here is never a 0, okay? And the same type of thinking or logic applies when we are dealing with binary numbers, okay? So the first digit for the mantissa is always a 1, except when dealing with what we call non-normalized numbers, okay? So the smallest value that can be represented in normalized fashion, okay? Here, actually, I think the Wikipedia page is probably the best resource here. Okay, so this is splitting up the thing. Okay, the smallest, what we call the normalized number, is you can have either a positive or negative 1, a 0 or a 1 for the sign. Okay, and then the exponent sign is going to be a 1, okay, and the smallest digits in the fraction field would be all zeros, okay, and so this basically represents we're multiplying times 2 to the negative 126 here, okay? Whereas, if we filled this all out with 1s, okay, we would get the largest, what we call normalized number here, okay, which would be raised to the positive 127. Now, we have to leave this, we can't fill out the exponent full of 1s, because if we fill out the exponent portion with 1s, then that takes on special meanings, okay? So pretty much when we're dealing with real numbers here, okay, I should format this a little bit prettier. So anytime you've got a number where the exponent for the 2 is between 1023 positive or negative 1023, then the value, the first digit in the mantissa is going to be a 1. If you put a 0 there, then that means you have to have a digit smaller than 2 to the minus 1023, okay? I feel like I'm not doing a great job explaining this, but so let me just say, okay, so let's say I want to just draw parallels to decimal notation, okay? So let's say you're limited to 10 digits in the fractional or in the mantissa, okay, and then you're limited to 2 digits with the exponent. Okay, I think it's easier to think in decimal form. Okay, so if you're limited to 10 digits in the mantissa and you're limited to 2 digits in the exponent, let's just think of to represent the value 1, what would we do? Okay, the exponent, as far as decimal notation goes, you would just have 1, and then you would have 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, you'd have 1 So you have 10 digits here. Okay, and then the exponent would be 0, 1, right? So that's to represent the value 1. Okay, and everything else is quite straightforward. To represent 1200, you would have 1.2, a bunch of zeros, and then your exponent would be 0.3. Okay, what is the largest value that can be represented? It would be 9.999999999 exponent 99, right? This would be the largest value that we can do. Okay, and then and we can make this plus or negative. Okay, what is the smallest value that we can have? And this okay, so we have a few ways to represent the smallest value. Or is this okay to represent the largest value in using the decimal note form? The smallest value in this form would be normalized. Okay, meaning we're kind of using proper scientific notation, would be 1 and then 0, 0, 0, 0, 0, 0, 0, 0, 0, and the exponent would be what? Negative 99. Okay, this would be the smallest value that we can have. Okay, we can have an even smaller value than this, and this would be the non-normalized. And what would that be? That would be 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, exponent negative 99. Okay, so you could have a normalized smallest value, but then you can also have a non-normalized smallest value. Okay, and so basically, if you just change it from decimal form into binary form, where you have zeros and ones rather than the digits 0 through 9, you basically have these same parallel forms. And I think it's a little bit easier to understand in the decimal form here. Yes, question?
For the largest value, is it a plus and a minus sign?
I mean, it could be plus or minus. Okay, I mean, so the largest value being the most positive value or the most negative value. Okay. Now, we actually do a couple special things to get to represent infinity, and we have infinity and not in numbers. Okay, so infinity is represented with, let me just double check here. So infinity is basically represented if the exponent is equal to 100, and I know that doesn't make sense when we say two digits with the exponent, but with the biased scheme, you can actually go from technically negative 99 to 100, right? So with the biased scheme for storing decimals. So limited to two digits with the exponent, but with the biased scheme, we're going from negative 99 to positive 100 because we get the extra spot with the by not having 0 represented in there twice. Okay, so if the exponent is 100, then we have infinity, but then everything has to be filled out with zeros. Okay, and then if infinity is represented with exponent 100, but all the decimals are represented with zeros. So we have 0.12345, 12345, okay? And then you can have a positive or negative infinity. And then if any of these is not a 0, then it becomes not a number. Is represented with exponent 100. And then one of these, one digit, is not a 0. Okay. All right, and so this is kind of, if you had to create a scheme using decimal notation where you're limiting yourself to the number of decimals to store and how many digits you can have, you'd have some kind of scheme like this. Now, we have the same parallel ideas, but just in binary. So instead of, exponent raised to the 99, it would be exponent raised to 1024 or 1023. Okay? So anyway, all this to show is that when you do certain calculations, okay, so the smallest number that we can represent would be 2 raised to the negative 16, and no, I'm sorry. We've got 2 digits for the 11 bits for the exponent and 52 bits for the mantissa, right? So we can have the exponent as small as possible and the mantissa as small as possible. Okay, so basically our non-normalized form. Okay, but in binary, that value is 2 raised to the negative 1074. Okay, so we cannot have any value smaller than this. So if I tried to raise it to 2 raised to the negative 1075, the computer sees this as 0. Okay, or if I tried to multiply this by any fractional component, well, actually that it can't distinguish. So if I try to take 2 to the negative 1074 and fractionalize it, it just goes out to 0. And actually, when I multiply it times 0.9, because of rounding, it just says it's equal to this. Okay, so I could say, is this equal to 2 raised to the negative 1074? And it says yes. Okay, even though mathematically we know this times 0.9 is not equal to this, but because the computer has to store it some way, and basically we're asking it is if I multiplied this digit, this number, by 0.9, but I'm limited to keeping 10 decimals, then I would write down the exact same number, right? Because in reality, I would have this 0.09, or with a 0.9 here, but I'm limited to 10 decimals, so I can't do that, okay? So you just have some interesting things. If I divide 1 by 2 raised to the negative 1074, that returns positive infinity, okay? If I try to add up a bunch of numbers, okay, so if I have 2 raised to the 1023, I have that, okay? 2 raised to the 1024 is infinity, okay? 2 raised to the 1023 plus 2 raised to the 1022, it can keep track. But if I plus, let me just do 2 raised to the 1022 minus 1. Or actually, is this gonna count? No, it can't do it. Okay, but yeah. So if I try to add anything here, it freaks out. Yeah. Oh, okay, no. Okay, so these are just, as you reach the upper and lower bounds. So 2 raised to the 1023 is somewhere around here. Okay. So as you reach kind of these upper and lower bounds, just the computer might just say, now you have infinity or 0 or things like that. So these are overflow and underflow errors because the computer just can't keep track of these numbers anymore. Okay, it's limited in how it's stored. This if I raise something to the to a very small number, okay, and I add it to 1, it can't keep track of it. It loses sight of it. Okay, so if I have 1 plus 2 raised to the negative 52, okay, it sees this. It prints out 1, okay, but it's not actually equal to 1. So I can store this as x, and x looks like 1, but if I say what is x minus 1, it says, oh, you got this really small number. Okay, so that's correct. Okay, but if I add on something else, oops, and I say this is y, and I add on 2 to the negative 53, okay, and I ask what is y, and I do what is y minus 1, then it says 0, okay? And so this is basically known as machine epsilon, okay? It's like the smallest value that that you can kind of tack on to 1 or something, and the computer can tell the difference between that and another thing, okay? And so you run into problems. So I can say, what is 0.1 plus 0.2? And the computer says it's 0.3, okay? And I can say, x, we'll say z is 0.1 plus 0.2, okay? And I ask, what is z? Z is 0.3. And then I can say later on, is z equal to 0.3? And it says no, okay? And that again is, the reason for this is the same problem that we had back here. When it's inside the computer, it's seeing something like this. It's not exactly 0.3. It's 0.2999 or whatever in the machine code. It's represented as something else, and so it can't distinguish between. I mean, it sees this as not being equal to 0.3, okay? And so you have a function called all.equal, and you can say is z equal to 0.3, okay? And then it will say yes, the answer is true, okay? And so all equal has kind of this tolerance that just says if these two numbers are within the tolerance of each other, we're going to say they're equal to each other. Now mathematically, that might not be the case, okay? So, we could say, what is pi? Pi is 3.141593, okay? Let me see if I could do format pi and decimals equal to 10. Oops. I don't know. How do I print out more decimals? Okay, but I can ask, is all equal pi and 3.141593. Okay, so this will say they're not equal. There's a small difference here. Okay. Okay, let me see. Is all dot equal pi and 355 divided by 113. So that's an even smaller difference. And you can use the all equal function, which is very useful in R calculations or math calculations, but it might not necessarily be mathematically true. Okay, so don't try to prove some kind of mathematical theorem using the computer. All right, that's never a good idea. But as far as when you're performing some of these numerical methods, and just you want to know, is this equal to something else? You have to keep in mind the machine error, meaning the machine can't store all of these digits. It can't distinguish between, it doesn't know that 0.333 up to 10 decimals is actually the same, should be represented as 1/3. Okay, it doesn't know that, and so when you code things up, you're just using these, are these two things equal? You could run into to some issues there that are confusing there. Okay, so I do recommend reading. I'll post up the notes here. Recommend reading this article on how digits are stored in a computer, and it seems boring, but it's very good. And then and I'll also link something called catastrophic loss of significance, which basically if you're limited to the amount of digits you can store, and you start taking differences between numbers, you might lose a significant amount of significance in your calculations as well. Okay? All right, well, we'll see you guys next week. Enjoy your Thanksgiving break and whatnot. I think right now teacher evaluations are available on my UCLA, and so I just want to ask you guys a favor to complete your evaluations, especially as a first year as a full-time lecturer. Those evaluations are very important, I guess, for my future career trajectory. So so I appreciate you taking the time to fill out those evaluations, and I hope you've enjoyed the course. So all right, so enjoy your weekend. We'll see you guys next week.